Have you ever built a snowman, or splashed in a puddle, or felt the wind on your face? If you have, then you already know the three most famous states of matter: solids, liquids, gases. Think of them like different dance parties for tiny little particles called atoms. Solid. In a solid, like the ice in your snowman, the atoms are packed together very tightly. They are like dancers holding hands in a perfectly still line, just wiggling a tiny bit in their spot. They can't move around or change places. Solid example, rock. Solid example, table. They are organized and super predictable. Now let's turn up the music for the liquid dance party. Liquid. In a liquid, like the water in that puddle, the atoms have more energy. They are still close together, but they can slide and glide past one another. They take the shape of whatever container they are in. What happens when we turn the music all the way up? We get a gas. Gas example, the air you breathe, steam from a hot kettle. They are like dancers at a wild party, bouncing off the walls and each other, spreading out to fill any space they can find. You might have heard of a fourth state of matter called plasma. It's like a super-duper hot gas, so hot that its atoms break apart. You can find plasma in stars, like our sun, and in lightning bolts. It's awesome and incredibly powerful. For a long time, plasma was the cool, edgy cousin in the family of matter. But scientists kept wondering, if you can find new states by getting things super hot, what happens if you go the other way? What happens if you make things colder than anything you could ever imagine? Colder than the coldest winter day in Antarctica? Colder even than deep space? This is where our story gets really, really cool. Literally. When you make things incredibly cold, just a tiny fraction of a degree above the coldest possible temperature, called absolute zero, something amazing happens. The wild dance party of atoms starts to slow down. They lose almost all their energy and start behaving in very strange ways. Instead of acting like individual particles, they start to act together as one giant, single entity. Scientists call this a Bose-Einstein condensate, or BEC for short. This is our fifth state of matter. It's a whole new world where the rules of everyday physics don't apply anymore. Imagine all the dancers at the party suddenly stop doing their own moves. Instead, they all start doing the exact same dance, perfectly in sync, moving as one giant wave. You can't even tell where one dancer ends and another begins. That's what a BEC is like for atoms. They lose their individual identities and merge into a single superatom. Albert Einstein predicted it in the 1920s, but no one made one in a lab until 1995. It was a discovery that changed everything. So now we have 5 states of matter: the solid, the liquid, the gas, the superhot plasma, and the supercold Bose-Einstein condensate. Each one is a unique way for atoms to arrange themselves and behave. But the story doesn't end there. The discovery of the BEC opened up a brand new chapter in science, a playground where the strange rules of quantum mechanics become visible. And in this super cold playground, they found something even more bizarre. Before we can understand our next amazing state of matter, we need to talk about the quantum world. The quantum world is the universe on the tiniest possible scale. It's the world of atoms, electrons, photons, little particles of light. And in this world, things are weird. Really weird. Particles can be in multiple places at once. They can pop in and out of existence. They can act like both a solid particle and a flowing wave at the same time. It's a place where all the rules of our big everyday world get thrown out the window. It's like a magical funhouse where nothing is quite what it seems. Normally we don't notice this quantum weirdness because it's so tiny, like trying to see threads in a giant tapestry from a mile away. But when we create a Bose-Einstein condensate, we make the quantum world visible. By cooling atoms until they act as one, we create a giant quantum object. All that hidden weirdness becomes the main event, like getting a giant magnifying glass to see the secret rules of the universe. One of the strangest things is a superfluid. A superfluid is a liquid that has zero viscosity. Viscosity is how thick or sticky a liquid is. Honey has high viscosity, water has low viscosity. A superfluid has no viscosity. It can flow forever without slowing down or stopping. It can even climb up the walls of its container and spill over the top. This happens because there's no friction to slow the atoms down, a result of all atoms acting as one single wave in a Bose-Einstein condensate. Seeing a superfluid is one of the most mind-bending things in science. It's a real-life magic trick, performed by nature. Get ready for the main event. Imagine an ice cube. It's a solid, right? It's hard. It keeps its shape. Its atoms are locked in a perfect repeating pattern. a crystal lattice. Now imagine that same ice cube, but with a twist. While most atoms are still frozen in their perfect crystal pattern, a few of them break free. They start flowing right through the solid crystal, like little ghosts passing through walls. They move without any friction, just like a superfluid. You would have a single object that is a perfectly ordered solid and a frictionless, flowing liquid at the exact same time. This, my friends, is a supersolid. It's a solid that flows. A crystal that's also a liquid. It breaks the fundamental rules of what a solid or a liquid should be. A solid is supposed to be rigid and stay put. A liquid is supposed to be messy and flow. A supersolid does both. It has the rigid, ordered structure of a crystal, but also particles that can flow through that structure without resistance. It's a true paradox of nature. For decades, the idea of a supersolid was just a wild theory. Scientists dreamed it up on paper, predicting that if you could make a solid cold enough and put it under the right conditions, this could happen. They thought frozen helium might be the perfect candidate. They ran experiments for years, sometimes thinking they found it. But then it would turn out to be something else. It was a scientific ghost hunt. But then, in the last few years, scientists finally did it. Using super-cold Bose-Einstein condensates, they created the first real, undisputed supersolids in their labs. Crystal patterns while also flowing like a liquid. The ghost had finally been caught. So, how exactly do you make a supersolid? Well, you can't just pop something in your freezer and hope for the best. The recipe needs the coldest temperatures in the universe. The main ingredient is a special cloud of atoms, often dysprosium or erbium. These are magnetic atoms, tiny bar magnets with north and south poles. That's the secret sauce. First, scientists trap a cloud of these atoms inside a vacuum chamber, then use lasers to slow the atoms down. Temperature is how fast atoms move. The lasers act like an atomic speed bump, stealing their energy and cooling them, millions of times colder than deep space. But even that isn't cold enough. Next comes evaporative cooling. Like stepping out of a pool, the fastest molecules leave and take heat with them. Lower the trap edges so the hottest atoms escape, and the rest get colder. The atoms collapse into a Bose-Einstein condensate. This is where the magic happens. The atoms act as one. Scientists carefully tweak magnetic fields. Because the atoms are tiny magnets, they attract and repel each other in a delicate balance. They form tiny droplets that line up into a repeating crystal. Yet it's still a superfluid, so atoms flow between droplets without friction. A solid crystal made of flowing superfluid. A perfect, freshly baked supersolid. Section 6. Making supersolids with light. If making a supersolid out of super-cold atoms wasn't mind-blowing enough, scientists can make a similar state using nothing but light. Light is made of photons. Normally, photons don't interact, cross two beams and they pass right through. They're the ultimate introverts. Scientists force them to interact using two ultra-shiny mirrors placed close together. Shine a laser in, trap photons bouncing millions of times, add a dye so photons get absorbed and re-emitted. This makes photons act as if they have mass and lets them talk to each other. Cool the system and cram in many dressed photons. They can form a Bose-Einstein condensate. Just like atoms, they merge into a single quantum state, a superphoton that acts like a fluid, a liquid of light that flows without friction. By cleverly manipulating photons in the cavity, scientists can make the fluid of light form a rigid, crystalline structure while also flowing, a photonic supersolid. Creating a true photonic supersolid is cutting edge, but the possibility is thrilling. These bizarre states aren't limited to atoms. They may apply to light itself. It hints at a deeper property of our universe. Order and flow, even in pure light. Section 7. How supersolids could build a supercomputer. All of this is incredibly cool, but what's the point? Today's computers use bits, tiny switches that are on or off, ones or zeros. All your photos, videos, and games are just long strings of these. Quantum computers use qubits. A qubit can be a 1, a 0, or both at the same time. Superposition, a superpower that could crush problems. Classical supercomputers would take billions of years to solve. But qubits are fragile, like soap bubbles. Tiny temperature changes, stray magnetic fields, even small vibrations can pop the bubble. That's decoherence, the biggest challenge. This is where supersolids come in. The rigid crystal structure can protect quantum information from noise, while the superfluid component lets particles move without friction to shuttle information around. Store qubits in the stable solid part to resist decoherence, then use the flowing part as a quantum data bus to make qubits interact and compute. Fast, efficient, with almost no heat. Current quantum hardware needs complex wiring for each qubit, impossible to scale. A supersolid-based quantum chip could be self-contained, with built-in protection and communication, paving the way to machines with millions of stable qubits. Section 8. The Quantum Chip Revolution. Imagine a new kind of chip, not silicon, but a tiny frozen supersolid. Quantum information encoded in its crystalline part makes qubits robust and long-lasting. The solid lattice is a silent shield against noise. Quantum computers could run much longer without errors. To do useful work, qubits must talk. The frictionless superfluid becomes the quantum data bus. Tiny pulses move information across the lattice efficiently. Instead of tangled wiring, this integrated design could scale from lab toys to massive machines with millions of stable qubits. A complete game changer. This is still a long way off. Today is October 3rd, 2025, and scientists are just beginning to master supersolid states. But the potential is enormous, designing new medicines, inventing novel materials, supercharging AI, and tackling global challenges from climate to food security. Section 9. Why supersolids matter for our future. From a simple snowman to a mind-bending solid that flows, our journey has brought us to the very edge of science. Supersolids are more than a cool party trick. They represent a fundamental shift in our understanding of the universe. For centuries, we thought solids and liquids were separate, like night and day. At the coldest limits, those boundaries blur and dissolve. The quantum world is stranger and more wonderful than we imagined. Chasing supersolids pushes technology. Better lasers, stronger magnets, colder refrigerators, and those advances reach our lives. Better imaging, more precise clocks, more powerful electronics. The dream of a supersolid quantum computer shows how basic research becomes world-changing. Solutions to huge challenges may hide in these quantum states. The path is long, but it starts with curiosity. A story of imagination, persistence, and surprise. Next time you see an ice cube in water, think about the incredible world of matter. Think about the solid that can flow, the liquid made of light, and the scientists exploring these frontiers. In that weird and wonderful quantum playground, they are building the tools that will shape our future.